All right, in the next part of 10.2, section 10.2, we're going to talk about converting back and forth between parametric and rectangular versions of the same graph, and specifically of the same type of equations. Now, the way we're going to do this is by substitution, but there's kind of two different types of substitution. One is a direct substitution, where we're going to solve down for a variable and then just substitute in for the variable. And then there's sort of an indirect substitution where we know some property of either trig functions, well, most likely it's going to be trig functions, or we know some properties of maybe exponential functions or something like that. So we know an identity, and we can utilize that identity inside the substitution process. Now, I'll make that clear in these examples that we're going to do. So, example 5 of section 10.2 says eliminate the parameter to get a rectangular equation. So this is the equation that we started with. In this section, x equals t squared minus 4 and y equals t over 2. Now we graphed that earlier and we saw that it was a parabola pointing to the right. So how would we be able to eliminate a parameter and end up with a rectangular equation? Well, here's how we would do it. We'd start with these two equations and we'd say, well, let's solve one of them. Instead of solving for y, let's solve one of them for, let's say, t. And the easier one in this case to solve for t is going to be the y equals t over 2. So what I do is I start with y equals t over 2, and I solve that, again, in a direct way for t. In this case, you'd multiply both sides by 2, and you'd end up with 2y equals t. Now, when you get 2y equals t, then you can take this other equation and plug in the expression 2y in for the t in the other equation. So we get x equals, and again, we're going to replace the t with the expression 2y. So hopefully that makes sense. We go x equals t squared minus 4, replace the t with the 2y we solved for the other equation. And if you want to clean that up a little bit, make that a little bit more algebraically, or make that a little bit easier on your eyes, maybe you call it x equals 4y squared minus 4, or maybe you put it in a standard parametric form, or did I say parametric? Standard form of parabola if you really wanted to as well. You could do that. I'm not going to do that in this case because it would force me to complete a square and do all that kind of stuff. I don't need to do those types of things right now. So there you go. No, it wouldn't. It actually would not force me to complete a square. That's almost in standard form already. Excuse me. So sorry about that. But anyways, the point is you can clean it up a little bit if you'd like. You can put it in slightly other forms if you'd like as well. So that direct substitution is going to be sort of the nicest way to do conversions. So I want you to try another problem and utilize direct substitution to eliminate the parameter and get a rectangular equation in this case. Push pause on the video and go ahead and do that. All right, hopefully you went ahead and did that. So here's what I'm going to do. I'm going to look at how I went ahead and did that. So in this case, it's probably going to be easier to solve for t with the y equation. If you do that, start with the y equation, y equals 7t plus 3. Subtract 3 from both sides, and then divide both sides by 7. You'll end up with t equaling y minus 3 divided by 7. Now, you're going to plug that in for your t in this other equation, By the way, that t is in the exponent, so it gets a little bit messy, but that's all right. So you go x is equal to, whoops, excuse me, e to the 2t minus 4. So you replace that t with a y minus 3 over 7. So e to the 2 times y minus 3 over 7. I distributed that 2 in. When you distribute that 2 into the parentheses, you get e to the 2y minus 6 divided by 7 exponent minus 4. Okay. Again, this is kind of an ugly equation, but it's still an equation um, in the rectangular form. So there you go, and that's fine. By the way, you could have also tried to solve this t by, adding 4 and taking natural logs, and you could have tried to solve in this equation too. It's just going to be a little bit more difficult to solve. Now, these first two equations were both, these first two equations of converting to rectangular were both sort of direct substitution situations. So let's get into the indirect substitution situations. Those are ones, well, again, we graph this, but those are ones like this, where we have x equals 8 cosine t and y equals 8 sine t. So what we're going to end up doing is we're going to do substitution, but I don't want to solve for t because then I have to do arc cosines or arc sines or whatever it happens to be, and then it becomes really, really messy. So what I'd rather do is say, well, notice that both of these, one of them involves a cosine t, and one of them involves a sine t. And so what equations do we know that involve cosine and sine of the same angle? If you think back, well, there's an obvious choice. Choice is our trig identity that we've seen before a lot in this class, which is cosine squared plus sine squared equals 1. Okay? So instead of solving this one all the way down for t, what we're going to do is solve this for cosine, solve this one for sine, and then plug those into the equations. Now I have to realize that what this is cosine of t squared and sine of t squared. So when I plug cosine of t in, I'm thinking of it as cosine of t quantity squared plus sine of t quantity squared equaling 1. So that's how I'm going to think about it when I plug things in. So we solve for cosine t over here. So take this x equals 8 cosine of t. That's pretty easy to solve for. Just divide by 8 on both sides. X equals 8 cosine t gives me that x divided by 8 is equal to cosine of t. Same thing for y. We take y equals 8 sine of t. So y equals 8 sine of t. Divide both sides by 8, and we get y over 8 is equal to sine of t. So now I have x over 8 is cosine, y over 8 is sine, and I plug it in to this identity. So take that identity, in for cosine of t, replace that with x over 8, in for sine of t, replace that with y over 8, and this is the equation you get. Now, I'm going to clean that up to make that look like a circle because I know that's going to come out as a circle. So you'd end up with x squared over 64 plus y squared over 64 is equal to 1. Multiplying everything by 64, you'd get x squared plus y squared is equal to 1. Okay? Or did I say 1? Excuse me. X squared plus y squared equals 64 when you multiply everything by 64. So there you go. And now you can see why when we graphed those parametric equations, why they had to be a circle of radius 8. Because of this trig identity, cosine squared plus sine squared equals 1. All right. And by the way, I forgot to mention this, but I tend to leave equations in the way I know them best. So if I'm talking about circles, I'll leave them in a circle form of an equation. If I came out with an ellipse, I'd leave them in ellipse form, those types of things. In a parabola, I'd make it a parabola form. So there you go. So what I'd like you to do is push pause on this video and try out example 8 on your own. Hopefully you went ahead and did that. So we're talking about 5 secant t minus 1 as your x equation, y equals 7 tangent t plus 7. So although we don't have an identity with tangents, well, we have an identity with tangents and secants, and that is the identity that comes out of dividing both sides of this cosine squared plus sine squared equals 1. Divide both sides by cosine squared. If I divide cosine squared by cosine squared, I end up with 1. Sine divided by cosine is tangent, so sine squared divided by cosine squared is tangent squared. And 1 divided by cosine is secant, so 1 divided by cosine squared is secant squared. So we're going to use this identity, and we're going to solve this trig identity here, and we're going to solve this x equation for secant, solve this y equation for tangent, and then use this identity and substitute out with what we have. Now, solving x for secant, fairly straightforward process. We're going to add 1 to both sides. You get x plus 1 equals 5 times secant. Then divide by 5 on both sides. You get x plus 1 over 5 is equal to secant. You do almost the exact same thing for y. Y equals 7 tangent plus 3. Subtract 3 from both sides. So y minus 3 equals 7 tangent t. And then divide by 7. Y minus 3 over 7 is equal to tangent. Now we go and we substitute into our equation 1 plus tangent squared equals secant squared. Tangent now gets a y minus 3 over 7. Secant gets x plus 1 over 5. And then if I clean this up a little bit, first step you could do is subtract this y minus 3 squared. Subtract that on both sides. And what I've done is I've just distributed that squared exponent to the top and to the bottom. So it looks like x plus 1 squared over 5 squared. By the way, 5 squared is 25. And then y minus 3 squared over 7 squared. And obviously 7 squared is 49. Now, this is pretty clearly a hyperbola. If you can't see it right there, then you can just put the equal 1 on the other side, and this matches the standard form for a hyperbola. And so that's why when we graphed that a little earlier, that we ended up with graphing this parametric equation, these parametric equations, and ending up with a hyperbola. So we ended up using secants and tangents in our parametric equation and getting that hyperbola. And this is why we have to get it, why it has to be that way, is because of those trig identities. Now, we obviously don't always have to convert into rectangular. We can go the opposite way as well. We can convert to parametric. And this works in the exact same way. We're going to have sort of what I call a direct substitution and then an indirect substitution. This We can say y equals x squared minus 4x plus 7. This rectangular equation probably would call for just a direct substitution. And we do have some options here. We can basically, no matter what we call x could be equal to t, x could be 3t, x could be 4t. Whatever it is, x could be any function of t, and then we just plug it in here and here and end up with y as a function of t as well. Let me go through that, or at least what I mean by that. So all I have to do is write x equals some function of t. I don't even care what it is, that function of t, so much. Although there's pretty easy choices, pretty hard choices as well. So if I let x, for instance, be t, you go y equals, and then everywhere you see an x, you just replace it with a t. So y equals t squared minus 4 times t. Now I put things in parentheses. Obviously, when you do that in a regular case, you don't have to. But you get a pair of parametric equations, x equals t, and y equals t squared minus 4t plus 7. Okay? So that set of parametric equations would graph and give you the exact same graph as this. Now that is not the only choice we could have done for t. We could have said, well, let's let x be 3t or 3t minus 1. And then all we would have had to have done is everywhere I see an x here, replace it with a 3t minus 1. Now this is a little bit more complicated of an equation, but it still gives us a parametric equation which has the same graph as this graph. And by the way, these two parametric equations have the same graph, this one and this one. However, it does, as you increase by t over here, you're doing something slightly different as you're increasing over here. In other words, this one, you're going to draw at a faster rate, if that makes sense. So this one, you go at a slightly slower rate. Let me give you what I mean by that. Actually, in this case, before I talk about what that means, let's actually agree that instead of using x equals 3t minus 1, because that'll be a shift, that minus 1 will shift. I don't want to do that. Let's let x be 3t, and then y equals this. All right, which, by the way, if you want to make that a little bit simpler, you could go y is equal to 9t squared minus 12t plus 7. Okay, so I'm going to graph both of these parametric equations on my calculator, both the x equals t version and the x equals 3t version. And we'll do a little work on how you would, how you can see that. What I've done here is I've tried to give you a graph of this. I've graphed y equals t squared minus 4x plus 7. That's the parabola that's in black here. And then I've let t be 0, and I've using the parametric equation where x is t and y is t squared minus 4t plus 7. That's going to be a blue dot, and then there's a red dot with x as 3t and y as 9t squared minus 12t plus 7. Now what you're going to notice is that when t is 0 here, the dot is right there. As you move to the right, as you increase your x value, notice that that red dot is moving further. I misspoke. As you move to the right, you're increasing your t value. So the x value on the red dot is increasing faster than the x value on the blue dot. So as you keep moving to the right, more and more and more, as you keep increasing your t, that red dot starts moving faster, And obviously that blue dot will start moving pretty fast, but the red dot is moving at 3 times the rate as the blue dot. And if you move backwards, it's the same way. The red dot is going to move at 3 times the rate as the blue dot. If I put this in motion, so you'll see how much faster that red dot moves than the blue dot does. All right. So that is what's going on. So when I say move faster, that's what I'm talking about. I'm talking about the speed at which, as you increase the t, the speed at which your x is moving and your y is moving. All right, so what you see there is that there's lots of different parametric equations that give you the same graph, and the difference is how the dot moves along the graph. So here's what I'd like you to do. I'd like you to push pause on the video and go ahead and do some substitution to create parametric equations for the following. Just create one set of parametric equations for the following rectangular equation. Specifically, y equals 17 times e to the 4y. Now, in this case, again, there's lots of choices you can do, but probably the easiest choice is to just let this y be your t. That's probably going to be the easiest thing. And then just set x equals, replace that y with the letter t. So 17 e to the 4t. That'll be the easiest one. If you wanted to, you can let t be, or excuse me, you could have also, this is kind of a nice one, y equals 1/4 of t. Whoops, let me do it the other way. 1/4 times t. And so when you plug in 1/4 t into your exponent, you get x is equal to 17e, well, 1/4 times 4 is 1, so you get e to the 1t. So that's a nice one too. You can make that again more and more complex if you'd like. And again, these are this pair of parametric equations, this pair of parametric equations will give you the same curve, but your point is going to travel at different speeds along that curve. Now, that's the direct substitution kind of way to go from rectangular to parametric. We can also do the indirect substitution when we have a situation like this. Notice this is an ellipse. We have the standard ellipse form. This is pretty easy to convert to parametric equations using the cosine squared plus sine squared equals 1 identity and indirect substitution. Why don't you try to do that on your own, and then I will show you how to do that as well. Hopefully you went ahead and did that. So we start with x minus 4 squared over 25 plus y plus 2 squared over 4 equals 1. I should think cosine squared plus sine squared equals 1. That's almost of that form. All I have to do, what's going on there? All I have to do is kind of come up with a form for cosine, come up with something squared for sine. Be a little bit careful about this. When you create this equation, you're going to create an equation with a single fraction being squared. So be careful with that. So instead of doing an x minus 4 over 25, what you want to do is you want to put x minus 4 over 5 and square the whole thing. All right? And then instead of putting y plus 2 over 4, what you're going to do is you're going to put inside, we're going to have a fraction of something squared equals 1. So we're going to have a y plus 2 over 2 quantity squared. Okay? Now we're matching this up with the cosine squared plus sine squared equals 1. And if you can see it from here, what this means is that the parametric equations, well, this first fraction, x minus 4 over 5, is going to have to be equal to cosine of t. And that second equation, y plus 2 over 2, let me go through that, is going to have to be equal to sine of t. Now, to get a parametric equation, we need an x equals and a y equals, but that's pretty easy to solve. Just on the x minus 4 over 5 equals cosine, multiply by 5 on both sides, and then add 4. So if you multiply by 5 on both sides, you end up with x minus 4 is equal to 5 times cosine of t. And if you multiply by 2 on both sides for the y plus 2 is equal to 2 sine of t. And then we can, for the x's, x minus 4 equals 5 cosine t, add 4 to both sides. 5 cosine t plus 4 is what x has to be. And if I subtract 2 from both sides of the y equation, we get y equals 2 sine t minus 2. So we see that this pair of equations gives you your pair of parametric equations for the ellipse that I had above. So that's how you do parametric equations with indirect substitution. I want you to try one more example of that. I want you to push pause on the video and try this. Obviously, the equation that the identity that we're going to use has to do with secants and tangents. We start like we always do, cosine squared plus sine squared equals 1. Divide that by cosine squared. You end up with 1 plus tangent squared t equals secant squared t. Now I'm going to rewrite this so it looks more like this equation. If you do that, what you need to do is you need to subtract tangent squared from both sides. You get secant squared minus tangent squared equals 1, or you can just say secant squared minus tangent squared equals 1 that way as well. So it's pretty obvious what we have to do. We have to convert this thing into this y plus 5 squared over 49 into one fraction being squared. And again, the conversion is a pretty straightforward one. We're going to take some fraction, square it. We need that. On top, it's going to be y plus 5. On bottom, it's going to be 7. Minus, again, a fraction squared. So what this fraction will be is x minus 8 over 6. And there we go. So all we have to do is set secant equal to y plus 5 over 7 and set tangent equal to x minus 8 over 6 and solve for each part. All right, so I've done that below here. I've set y plus 5 over 7 equals secant. X minus 8 over 6 is equal to tangent. And then solving for each, you'd multiply by 7, then subtract 5 from both sides. For the y equation, you'd end up with y equals 7 secant t minus 5. And for the x equation, multiply by 6 and then add 8. So you get x equals 6 tangent t plus 8. And that would be your pair of parametric equations that give you the hyperbola that you started with. Again, and this was a hyperbola, standard form of a hyperbola. So there you go. That's how you would convert back and forth between rectangular and parametric equations.